For most of human history, the oceans acted as enormous barriers between continents. The Americas are a clear example, as rising sea levels submerged the Bering Land Bridge around 10,000 to 11,000 years ago. The overland connection between Asia and the Americas disappeared. From that point on, the peoples of the Americas remained separated from the networks of Eurasia and Africa for thousands of years. To travel long distances by sea, at a time when engines were still thousands of years away, there were basically only two available sources of propulsion: human power and wind. You can cross the sea using oars. Civilizations did it for thousands of years. But there is a problem. Every rower has to be carried along with the ship. He takes up space. He needs water. He needs food. He complains when he gets tired. And unlike the wind, he keeps burning through fuel even when the ship is standing still. A sailing ship, by comparison, only needs ropes, masts, and fabric to harness its power source. The energy itself is outside the ship. That frees up space and allows a vessel to remain at sea for much longer periods. And in that sense, wind powered the first age of globalization. Humans began moving armies, goods, religions, languages, diseases, and technologies between parts of the world that had remained separated for thousands of years. It's hard to overstate the consequences of this. By around the second millennium, a large share of intercontinental trade across the Indian Ocean was already moving by sea. Centuries later, sailing ships would support the networks that connected nearly every major ocean on the planet. Without another technology capable of replacing wind power, doing this on a large scale would have become extraordinarily difficult. There is no serious answer to the question, how many years would this have set the world back? It could have been decades. It could have been centuries. Another solution might have emerged sooner, but some of the consequences are easy to imagine. Columbus would have been far less likely to make his Atlantic crossing in 1492. Portuguese expansion down the coast of Africa and later into the Indian Ocean would also have been far more limited. And without an efficient way to move large ships across thousands of miles, much of large-scale oceanic expansion might have had to wait for some form of mechanical propulsion. And that creates a strange possibility. Part of what we now call the Age of Exploration might have been pushed much closer to the Industrial Revolution. Remove the sail from history, and you also change the timeline of globalization. In 1794, a British naval writer and publisher named David Steele published a work called The Elements and Practice of Rigging and Seamanship. In it, he documented nearly every aspect of the technology behind a large sailing ship: how to make masts, cut sails, manufacture rope, assemble the rigging, and then put all of it to use at sea. Steele was writing at a time when these ships were still cutting-edge technology. The result is essentially a technical manual for the great sailing ships of the 18th century. A large part of the technical explanation in this video is based on that work. A sail seems simple. A huge piece of fabric is attached to a mast. The wind pushes against it and the ship moves. With the wind coming from behind, the explanation can be almost that simple. But what happens when the wind comes from the side? First, we need to separate two things. There is true wind, which is the movement of air relative to the surface. And there is apparent wind, which is the airflow experienced on board the ship. As the ship begins to move, its own motion changes both the direction and the strength of the wind reaching the sails. And that apparent wind is what the sails are actually responding to. The sail can be set at a specific angle to that wind. As air flows past it, the sail deflects the airflow and creates an aerodynamic force. That force acts at an angle. One part of that force pushes the ship forward while the other pushes it sideways. And this is where the submerged part of the ship comes into play. The hull and the keel resist that sideways motion. Think of the difference between sliding straight ahead on skis, which is relatively easy, and trying to push them sideways, which is much harder. The ship still drifts slightly downwind. This sideways drift is called leeway, but much of that lateral movement is resisted by the water. So, the system works like this. The sail creates a force at an angle, the water resists the sideways motion, and part of that force is able to accelerate the ship forward. Aerodynamics explains the force produced by the sail. Hydrodynamics explains why the ship is not simply pushed sideways. And it is the interaction between the two that allows the ship to move forward, even in a direction that is partly against the wind. This region is called the no-go zone. If the destination lies directly upwind, the ship has to work its way around it. It sails diagonally on one tack, then turns and continues on the opposite tack. That turn is called a tack. During the maneuver, the rudder brings the boat through the wind, while the yards, sails, and lines are adjusted for the new tack. Once the sails fill from the opposite side, the ship continues moving forward. Then the process repeats, creating a zigzag course. This process is called tacking. The closer a ship could sail to the wind without losing speed, the tighter its zigzag course could be. A tighter zigzag meant less distance to cover to reach the same destination. So two ships facing exactly the same wind could arrive at very different times simply because one of them could point a little higher into the wind. That may sound like a small advantage, until there was another ship trying to get there first, or trying to shoot at you. In naval warfare, there was one particularly desirable position, the weather gauge. Basically, it meant being upwind of the enemy. The ship to windward often had greater freedom to dictate the action. It could close the distance or remain where it was and make it more difficult for the enemy to leeward to force an engagement on the same terms. That turned what seemed like a small difference in upwind performance into something much more serious. Over the centuries, different sail shapes and rigging systems emerged to solve different problems. The square sail, or more precisely a square-rigged sail, was extremely effective at presenting a large area of canvas to favorable winds. But there were also fore and aft sails. One of the most important was the lateen sail. It was attached to a long angled yard and could be positioned differently from the large square sails. There is evidence of lateen-style rigs in the Mediterranean dating back to late antiquity, and they became widely used in the centuries that followed. Over time, large European sailing ships began combining different solutions. Large square sails provided enormous sail area, while triangular staysails appeared between the masts and toward the bow. Near the stern, fore and aft sails helped with balance and maneuvering. One sail might provide raw power, another might be more useful for controlling where that force acted on the ship. The result was not a random collection of canvas. Knowing how to sail against the wind did not mean sailors enjoyed doing it. Beating to windward is the maritime equivalent of skating uphill. It works, but it takes far more effort, and everyone hates every second of it. If there was a way to make the atmosphere do the work for free, sailors were going to find it. And this is where the planet's invisible engineering comes in. Earth's atmosphere is not completely chaotic. It follows large-scale, predictable patterns. Near the tropics, global atmospheric circulation and the rotation of the planet produce the trade winds. Essentially enormous, predictable conveyor belts of air that blow in broadly consistent directions. They made ocean routes predictable enough to be repeated voyage after voyage. The Portuguese looked at this system and developed one of the most counterintuitive maneuvers in the history of navigation, the Volta do Mar. The logic was basically this: if a sailor was off the coast of Africa and wanted to return to Portugal, the straight line on the map pointed north. The problem was that the wind was coming straight from the north. The obvious solution would be to fight your way up the coast. But the Portuguese solution was to turn the ship out toward the open Atlantic, sail westward in the general direction of Brazil for weeks, make a huge sweeping turn in the middle of the ocean, and let the winds carry them back toward home. In the Indian Ocean, the monsoons changed the prevailing wind patterns with the seasons. During one part of the year, the winds favored travel in one direction. A few months later, the pattern reversed and favored the return voyage. Trade routes between India, Arabia, and Africa took advantage of this regular cycle for centuries. That meant the wind did not determine only where you sailed. It also helped determine when you left. A merchant could have the ship, the cargo, the crew, everything ready to go, and still have to wait for the atmosphere to change its mind. Sailors were not just choosing routes across the ocean, they were choosing routes through the atmosphere. A sail laid out on the floor of a sail loft is completely flat. The moment it is hoisted and hit by 30-knot winds, the fabric stretches, the seams give slightly, and the sail has to take on the precise three-dimensional shape of an aerodynamic surface. If the sailmaker cut the cloth too flat, the sail would not generate enough lift. If he left too much fullness in the wrong places, it would become baggy and could collect water. Large sails were made from multiple strips of canvas sewn together, but the wind did not distribute the load evenly. The edges, and especially the points where the rigging pulled on the sail, were subjected to much greater stress, so those areas had to be reinforced. Additional strips and layers of canvas were sewn over specific sections of the sail. Along the edges, a heavy rope was sewn directly to the canvas, the bolt rope. Along the top was the head rope, along the sides the leech ropes, and along the bottom the foot rope. At the corners were reinforced attachment points where important lines connected to the sail. The wind was pulling on almost the entire surface of the sail. The rigging was pulling on specific points. Those points had to survive that tug of war, so they received extra canvas, rope, and reinforcement. Even the way the individual panels were cut mattered. A sail lying loose on the deck did not have exactly the same geometry as that same sail stretched under wind pressure. The sailmaker had to anticipate how the fabric would deform once it was hoisted, where to reinforce it, where to cut it, where to sew it, and where to place each eyelet. A sail was a flexible structure engineered to transmit enormous loads without tearing itself apart. If a sail can move the ship, why use so many of them? Dividing the total sail area among multiple sails made it possible to add or reduce power gradually. Light winds? Set more sail. Strong winds? Set less. The largest sails were carried lower down. Above them came progressively smaller sails. This kept some of the weight away from the top of the rig and prevented too much sail area from being concentrated dozens of feet above the water. At the bottom were the large courses. Above them were the topsails. Higher still were the top gallants. Between the masts were staysails. At the bow were jibs, and toward the stern, other sails helped with balance and maneuvering. The ship did not have a throttle. It had a sail plan. A large traditional sailing ship had three principal masts running from bow to stern, the foremast at the front, the mainmast in the middle, and the mizzenmast at the rear. But none of these was necessarily one enormous, continuous piece of timber. Instead, each mast worked like a modular tower, built in sections stacked one above another. Lower mast, the massive bottom section, stepped deep inside the ship. Topmast, the second section, fitted and secured above the lower mast. Topgallant mast, the third level of the wooden tower. Additional sections. On some ships, the rig extended even higher, with sections such as the royal mast. Even the lower masts of the largest warships were often not made from a single tree. They could be made masts, built from multiple pieces of timber carefully shaped, fitted together, bolted, and secured with heavy iron hoops. Because expecting nature to provide an entire fleet with enormous trees that were long enough, perfectly straight, and free of structural defects would have meant relying a little too heavily on the cooperation of botany. Running across the masts were the yards. Each large square sail had its own yard, and the yards could be rotated. By hauling on the right lines on one side and easing them on the other, the crew could change the angle of the yard. The sail turned with it. That was how hundreds of square meters of canvas could be positioned relative to the wind. But that leaves you with three wooden towers, covered in yards and sails, standing on a platform that never stops moving. The solution was simple: rope. A lot of rope. Despite appearances, that forest of rope could be divided into two basic systems. The standing rigging kept the structure upright. The running rigging made things move. Shrouds, stays, and backstays supported the masts from different directions. The small horizontal lines running across the shrouds formed the rat lines, creating the ladder sailors used to climb the rigging. Then came the lines that actually controlled everything. The braces rotated the yards. The halyards raised them. The sheets controlled the sails. The lifts supported the ends of the yards. Other lines gathered in different parts of the canvas. So that absurd amount of rope had a fairly simple explanation. Every movement needed a line. Turn, raise, lower, tighten, ease, gather. Today, many of those movements would be handled by motors or hydraulic systems. On these ships, the control system was built mostly from hemp rope and human muscle. And human muscle came with some pretty strict limitations. A rope transmits force, but there is a limit to how much force a group of men can apply directly, so instead of relying on superhuman strength, ships were packed with blocks, solid wooden housings containing grooved wheels or sheaves through which the ropes ran. A single block could simply change the direction of the pull. But combine several of them and you got a tackle, and a tackle allowed you to trade distance for force. In an ideal system, if a load is supported by two parts of the rope, the force required to lift it is roughly cut in half. Four supporting parts reduce the effort even further. The price is that you have to pull a lot more rope. This was the kind of mechanical advantage that allowed crews to handle 2-ton guns, tension heavy rigging, maneuver enormous yards, and move tons of supplies without destroying anyone's back. A tackle was an extremely simple machine. Wood, sheaves, rope. And yet it multiplied what a crew was physically capable of doing. While tackles solved the problem of moving heavy loads around the ship, a much larger force was constantly threatening it from the outside: gravity. The wind acts on the sails high above the waterline. That force tries to heel the ship over. To resist it, the center of gravity had to remain low enough. That is where loading and ballast came in. On large historical sailing ships, weight could be concentrated low in the hold, and the distribution of cargo, provisions, weapons, and ballast had a direct effect on how the ship behaved. Steele's own treatise discusses how the position of weight affected rolling, pitching, and the stresses placed on the masts and rigging. With a properly positioned center of gravity, the hull could generate a stronger riding moment as the ship heeled. But there was a trade-off. A ship that was too stiff could snap back upright with more violent motions. A ship with too little stability could heel too far. Even putting weight in the bottom of the ship was a compromise. More wind means more force on the sails. Up to a point, that means more propulsion. Beyond that, an increasing share of the force shows up as heel and structural load. The hull begins working at a less efficient angle. Leeway increases. The rudder becomes less effective. The masts and rigging are placed under greater loads. Eventually, carrying more sail produces far more strain than additional speed. The wind still has energy. The ship simply can't use it efficiently anymore. The solution was to reduce sail. A sail could be furled completely, or its area could be reduced by reefing. Reinforced bands ran across certain sails, with reef points that allowed part of the canvas to be gathered up and secured. In strong winds, carrying less sail could actually make the ship sail better. Less heel, more control, less structural stress, but part of that work still had to be done by men out on the yards. The old seafaring rule was, one hand for the ship and one hand for yourself. In a gale, however, hauling in frozen canvas that was snapping violently in the wind could take both hands, all while the entire rig swung through 40-degree arcs above enormous waves. That was one of the cruel paradoxes of the age of sail. The more dangerous the ocean became below, the more urgently men had to be sent aloft to save the ship. The sails also applied force at different points along the ship. The forward sails acted farther ahead of the hull's center, while the aft sails acted farther behind it. Changing that balance altered the ship's tendency to turn one way or the other, so the crew could assist the rudder by redistributing force between different sails. During attack, this became especially important. Some sails could be adjusted to help initiate the turn. Others were held or repositioned to keep the ship rotating and bring it onto the new tack. So the sails were not just the ship's engine, they were also part of its steering system. The ship's heading resulted from the combined effect of the rudder, the hull, and the distribution of aerodynamic forces across the sail plan. In the 19th century, naval design reached the height of its obsession with speed, the clippers. These ships were built for speed, long narrow hulls, extremely tall masts, and enormous sails that pushed them through the water. In the global tea trade between China and the West, arriving first was not simply a matter of prestige. Every day saved at sea could mean a fortune in premiums for the first fresh tea to reach ports like London and New York. Crossing the oceans was no longer just transportation. It had become a relentless race against time, but the engineering of wind power reached its most refined form at almost exactly the moment it was becoming obsolete. The Industrial Revolution introduced a source of mechanical power that did not care about the weather and did not depend on the cooperation of the seasons, the steam engine. With the opening of the Suez Canal in 1869, cutting the route between Europe and Asia through narrow, relatively calm waters, where large sailing ships were at a major disadvantage, steamships gained a decisive advantage on some of the most profitable trade routes in the world. Quietly but decisively, wind lost its place as the primary engine of global commerce, at least for now. There is an interesting irony in naval history. After centuries of replacing sails with engines, the shipping industry has started looking at the wind again. Modern commercial ships are already using auxiliary systems such as rigid sails, rotor sails, and kites to reduce fuel consumption. The International Maritime Organization even recognizes wind-assisted propulsion as one of the technologies that can help reduce emissions from shipping. By 2026, studies were already counting dozens of large commercial vessels in service equipped with some form of auxiliary wind propulsion. The materials have changed. The controls have changed. Computers can automatically calculate the best angle. But the source of energy is still the same. Moving air, and perhaps that is the most impressive part of the entire story. Today, surrounded by carbon fiber, digital sensors, and artificial intelligence, we are simply rediscovering something shipbuilders understood 2 centuries ago. The fact that naval engineering is returning to sails 200 years later may be the best proof that those machines of wood and canvas were never primitive. They were simply ahead of their time.